Okay, so today we have our own Professor Chunlei Guo giving the office colloquium. Most of you probably know him. In case there are some few people who don't know him that well, Chunlei Guo did his PhD in 1999 at the University of Connecticut, and he spent a couple of years as a postdoc at Los Alamos National Laboratory, and he came to UOPA in 2001. He joined the Institute of Optics, became one of us, and since then he's done a lot of good work. You might have heard about the, black metal and things like that. He has at least 4 times he's been featured in New York Times. He's also a fellow of the American Physical Society, Optical Society, or what we call optica, and the International Academy of Photonics and Laser Engineering. He is the editor-in-chief of a book from CRT Handbook of Laser Technology and Applications. And today he's going to tell us, Mr. in group, the last few years, I guess you're going to cover, right?
Yep.
Okay, with that, I'll let you go.
Okay. Everything goes well here? Okay. All right. Perfect.
Your pointer or the beginning pointer?
I don't.
You don't have pointer, right?
No.
Do you have pointer here? We used to have pointer here, but they always disappear.
It walked off after the last one, so you can use your pointer on here.
Oh, I see. You can use your
Okay.
pointer.
Okay.
Okay.
Okay. I'll just do that. Oh, okay. Okay, so thank you, thanks Golden for the introduction. And today, as the title of my talk indicates, I'm going to discuss 2 topics that are going on in my laboratory. And one is just like the title suggested, and one is using laser, the other one without. Okay. So looking at the outline. So if you're looking at the outline, so I'm going to start with, as Golden mentioned, some of you have known that my work involves using femtosecond lasers, nano-patterning a surface and study their properties. And today I'm going to go beyond that and discuss our more recent activity. I'll start there and also discuss our more recent activities about laser lithography. How do we use a femtosecond laser processing to create very tiny structures and highly regular that can somehow resemble what you can do with photo and LED photography? And then for the second part is, I will assume something that is lesser known to many, even any audience here, is we also have a active research area that does not use lasers. So I'm going to discuss, so particularly, and we're going to discuss a topic that is really trying to marriage the optical coating technology with more modern nanophotonics. We know thin film optical coating has been going on for centuries. And in fact, I believe our department is one of the very few in the country that actually teaches optical coatings. And so it's a very old science and old optical field. And there's a very mature. There's in other words, it doesn't really have any new things. It doesn't really emerge. The new thing doesn't emerge daily as other fields. Okay. On the other hand, nanophotonics, many people here know, it's a newer, very active field. So here, I'm trying to answer the question: can we actually really marry these two, like an ancient field, optical coating, with more modern nanophotonics? And we'll take a look at what will happen. Okay. And then we're also going to use the optical coating as a platform to also modulate the materials. And then the 2 topics I'm going to converge into the applications. So each of them has their respective wide range of applications. But here, just because of the time, I really have to be really watchful of the time. And I'm going to just select the type of application that is more renewable energy and sustainability relevant. Okay, so that's how I'm going to lay out my talk. So starting with somewhat familiar topics to many of the audience here about laser-based work and laser processing. So so I use my lab. We use femtosecond lasers. Okay, if some of the students don't quite know about femtosecond laser and material interactions, and we actually have a course, optical course 66. So you'll be, I'll be teaching the next semester. And if you are interested in this field, so that's something you can consider. So here are just some femtosecond lasers in my lab. You can see, you lift up the covers, they are very colorful. So femtosecond is 10 to the minus 5, 15 seconds. Very short pulse. Okay. So and number one is short. Number two, when you pack even a moderate amount of energy into such a short pulse, you can have a very high peak power. So we are utilizing those effects to study what's going on for material interaction. Well, indeed, I also like to add 466 used to be just ultrafast optics, but now we augmented into half of the semester ultrafast optics, half of the semester laser magnetite interaction. So our department has, I think for the first time, we have a laser magnetite interaction course. Okay, so why do we study laser processing? Well, there are many reasons. So here is a market report and provided by Strategies of Unlimited. So looking at the laser, the overall market of different sectors based on the laser applications, we can see material processing actually occupy the largest, over a third of the market. And the second one, right, slightly smaller will be communications. Okay. And then the rest of all the other applications add up to be just about the remaining third. Okay. And therefore, it's very important today, if you talk about lasers, laser applications, well, that's the market report tell you which area is the most important. So femtosecond lasers, because the short pulse duration, high peak intensity, just as I mentioned, when it's first started a few decades ago, and it's already people are naturally very drawn to utilize femtosecond lasers studying material processing. And at the very beginning, and what they're looking at is it's a micro machine. Okay. So they are use the femtosecond laser and try to create very precise cut, usually micron scales. So this is really a carving work, right? Use the laser beam, blast the sample, ablate the sample, and then you can carve out a certain structure. Well, here's on the right, here are some early works on the right-hand side, and the top and bottom are the comparison study between nanosecond long pulse laser ablation versus short pulse laser ablation. So it's cleaner, okay, about the same size. That's what's drawn people into a study laser ablation early in the days. And then naturally, people wanted to ask the question, well, can we push this further? We all know, I assume everybody know here, you have your optical beam, your laser beam cannot focus below wavelength, right? So that's the diffraction limit. And people wanted to push this and say, well, can we go to a smaller scale, really sub-wavelengths processing? Here are some early works. So if you're looking at all these examples I listed here, they are all based on, you cannot just use femtosecond laser alone, you have to add something else. So those are, for example, mass projection, near field ablation, you use the microscope, you use a chemical reaction, you use a certain assistant tools to try to make the femtosecond laser process the material at a smaller scale. So when I came here, the question I wanted to ask is if we can use a pure direct femtosecond laser alone to process the material and create tiny structures and really start beating the wavelength limit, the diffraction limit. And then, so that was the work, really at the very beginning, I was really focused on these very fundamental topics. I just wanted to look at how can we use some fundamental interaction to understand that, and we had a success. Right? And back in this is the actual review article. Actually, back in the first time, 2005, published the first paper and really were able to use pure laser beam alone and create the structures that are much smaller than the wavelength. So once again, I want to emphasize this is not through laser carving, right? So the laser beam will be very large, and typically your laser beam will focus at 100 micron level. So if this was the size of the actual structure of your laser beam, will be the size of the canvas. Okay, so we are creating the structure well within the laser beam. And through a lot of physical processes that I don't have time to get into, for example, so as plasmonic, launching their interactions. So with that, and we were able to really have a leg up to start exploring a range of technologies. It was early in the day. It was very exciting, and for the first time, we were able to utilize surface patterning and then pattern the surface, and then create this. You change the optical property and create this so-called black metal and color metal. So a shiny piece of metal, we can make it pitch black or to other colors. And so once again, this color is not through paint or pigments. It's not a chemical coating. It's purely structural coloring with all the micro nano structures. So if you were wondering how this could be,
okay, yeah. Thank you. So create this a very so it has a very a good educational effects, and quite a bit later on there's quite a bit newer scientific discovery was shot actually in my laboratory. So it's a good one to understand some of the basic things. So after black and color metal, we push the technology further. We're looking at how it's interacting with water. And here is the first one, and we create this so-called superhydrophilic surface. And then you can see it's a very strong attracting water. So if you put a drop of water at the bottom of the surface, the water actually runs uphill against the gravity. So basically here is a New York Times article suggesting we could use this cooling for a lot of applications. And actually, I'm going to discuss some of those works later on. Okay, later on, we developed this counterpart technology, superhydrophobic surface. So you can see the water droplet will bounce off the surface, will not be able to stick. Okay, so we had, if you're looking at some earlier structures, they're somewhat random. They're a small scale, very tiny scale, but they're a little bit random. So lately, we also push for a direction. We want to create a very highly regular and very highly tiny structures. So here's our endeavor in this direction. So you can see, starting from we were able to produce this very highly periodic 1D grid in 2D structures on metals and also on glass, other material as well. Here's on glass, on the scale I think this missing error bar is a 300 nanometer scale, definitely below the wavelength range. Okay. And another thing is, today we understand the mature technology for material patterning is lithography, optical, deep UV, E-beam lithography, ion beam lithography. But what's the problem? It's very expensive, right? So if you have done those research, if you want to pattern the surface at a scale of millimeter, it will cost you hundreds of dollars and hours after hour. If you talk about the larger scale, that's nearly impossible because you have to have this very complex involving, you have to have a vacuum chamber, open it up, and then put the sample inside and just do so much work. And if we use lasers, and all of a sudden we can dramatically enhance the speed and then make it much, much scalable. And we do this in different type of surfaces, can be on the curved surface and it's in the air, in the ambient environment. So here's another example to showcase the technology can be versatile. So the first, the A shows we can have the laser beam right in this structure. And then afterwards, and then we send another beam come here and erase the structure. Okay, you can see from C and D. And then afterwards, we can send in a third beam comes in and then rewrite the structure. So you can erase and correct and then modify. Okay, so here's another case, just showcase how we can push the technology. And this is, when I noticed this bar actually block all the references. Oh, how can I hide?
You can just go to the three dots here.
Uh-huh.
If one of the options is the hide this bar.
Okay.
Hide video kind of thing.
Meeting control?
Yeah, I guess so.
Okay. I hope it's okay. I didn't turn off the Zoom. Okay. So so here is basically a work. We actually did this on graphene oxide, and then only 150 nanometer thin layer. We use the laser to pattern the surface, and you can see create this very highly regular structures. So I'm going to spend.
Is there a pointer on your screen there somewhere? On the screen there must be a pointer somewhere, right? You can turn that on.
Let me see.
Generally, there's a pointer within the Zoom.
Okay. Yep.
Yeah.
Yep. I got it.
Yeah. Okay.
Yep.
Okay. So
Yep.
you can move that around.
Okay.
And that will work.
Yep. Okay. Yeah. Well, so far, most of the time, I don't feel I need a pointer. So, well, we afterwards, I'm going to discuss some applications in this topic. And then there's a lot of very obvious applications even before we just had the technology. And you can think of hydrophobic surface will be anti-corrosion, anti-icing, anti-fogging, and then some of those. Okay, those are obvious ones. And indeed, we actually have done work and published work and demonstrate. Oh, did I turn on this? Is my voice okay? I forgot to turn on.
Turn it on. I think that's what. Yeah.
Okay.
You don't need to turn it on for people in Zoom.
I do or do?
You do.
Oh, I do. Oh, okay. Wow. All right.
Okay.
So that's why early on somebody mentioned, yeah, I forgot to turn this on. Is it getting better? I don't notice difference. Is there a difference?
I think you'll only notice it if you're on.
Okay.
It's okay. It's okay.
Okay. Yep. Okay. So some obvious ones, right? So we did those, and then there's slightly less obvious ones. For instance, hydrophobic surface were antibacterial, and we demonstrated by growing E. coli. Try to grow E. coli on hydrophobic surface. We saw 99% suppression of the E. coli growth. Okay. And then there will be even we can use this surface to harness water from thin air and then pull out of the air water And then some of you may know, we have actually a project trying to use the hydrophobic surface for sanitation, for actually building a self-cleaning toilet. And we actually also did a fecal-phobic surface. We were able to achieve that. And although it looks gross, but those are fecal simulant. It's not the real feces. Okay. And then we actually collaborating with the China lab, we built a toilet prototype. All right, so but let me move on, really discuss some really energy related applications. So the first one I would like to discuss is so-called thermoelectric generator. So what is the so-called TEG? I'm going to start using TEG. Just remember, it means thermoelectric generator. What is a TEG? So TEG is usually you have basically two plates. You have a hot side on the top, cold side at the. I'm going to use. You have a hot side. You have a cold side. There's utilizing the temperature difference between the hot and cold side. You can generate electricity. Okay, that's easy. Okay. And therefore, well, usually what do you want for your hot and cold side? You want the thermal conductors, right? So very conduct the heat well, because this is heat-based devices. And actually TEG is very become increasingly important today. We know there's thermoelectrical devices. There's the bigger market is the photovoltaic, right? So photovoltaic silicon solar cells is everywhere, harness energy. But TEG is also become more important because it's not only can harness the solar energy, but it can also harness the waste heat. Think about you're driving your car, your exhaust pipe get right hot, and that heat can be really rightfully harnessed by the TEG device. Okay. And as I mentioned, you need actually a conductive material. So that's also good absorption on the hot side and good radiator on the cold side. And we have this. That's what we have, right? So we have a black metal. It's a metal conductor, and it's black. It's good at absorption. On the other hand, I think this audience should understand Kirchhoff law tells us a good absorber is also a good emitter, right? So you also emit the heat well. So we can have a good absorber on the hot side and also good emitter on the cold side. All right, so that's what we have. And we actually just bought a TEG device and from the market, and then we put our black metal on top and integrate our black metal technology, and we put a solar simulator and then start looking at this. And lo and behold, we see this, you can see the absorption immediately increase. And then here is a regular surface. It's a scatter everywhere. It's hard to see. When the black metal is here, it's clearly see. It's very bright solar light shine upon it. And then we got immediately, we got 130% increase just by putting the black metal on the hot side, okay? And there's more to it. We have to design, I'm oversimplified it. So we have to design a so-called selective solar absorber, not just black, but also minimize the IR radiation, okay? So if you are interested, here's I put all the reference here. You can go look them up. Well, what about cold side? And as I mentioned, the black metal is also a good emitter. So we could, we actually, pattern the surface, specifically want to enhance the emission. And then afterwards, we demonstrate we can enhance the aluminum emission efficiency by 700, a whopping 700%. And then we increase the radiative conductive cooling power by 21 times, okay, not 2% or 20%, 21 times. and then 3 times respectively at 200 degrees. And then we increase the TEG just right there by putting this piece of radiator on the cold side. We increase by almost three times. And again, here's the reference. So the next question is you might ask is, what if I combine the hot and my cold technology? Can we add it up to like one is 100%, the other one is 280%? Indeed, this is the research actually going on in the lab. I don't know if Tianshu is here. Here's a runway. Okay, here. They are working on this. Indeed, we saw we can dramatically enhance this efficiency by really add them up. Okay, and the next one.
How much does it cost in fees? How much does it cost in fees for thermoelectric device you bought? You did those 2 things.
Right.
How much more expensive it would be?
Right.
4 times, 5 times, 6 times, what's the number there?
So the technology it does. I can. Today you're looking at the laser is really relates to how well developed the laser technology. So 5-10 years ago, I think it will be expensive, and you'll probably see it's expensive. But today is actually dramatically we can increase the speed and cut down the cost. We actually have a spin-off of the lab. They are looking at pattern surface 1 meter by 1 meter size within hours. So today, pattern surface will be dramatically faster than it used to be. Yeah. So the next I'm going to, how is my time going in this?
You're halfway left.
So now I'm halfway through. Okay. Just want to gauge my time. And so here is a work we are really actively pursue in the lab right now. Subhash is sitting here. He's really leading the research efforts in this direction. So we utilize our superhydrophilic surface, black metal, and then we want to looking at sanitation, water evaporation. Well, first thing you might ask is, what are you talking about? Water evaporation? This is simple. Yeah, you just put a pot of water on the stove top, then you evaporate the water. Yes, but you can do that, but it's very low efficiency, right? Think about this. You have to heat up the whole volume of water, but what is evaporate? Only the top layer, right? Micron level layer. You might not really think very carefully about this. So it's not efficient. You supply all the energy and only heat up the top layer. Therefore, people start thinking about, you can actually do a so-called interfacial evaporation. So you just take a top layer and only heat up there, the top layer. Don't heat up the bottom, the lower volume, right? So this is actually very active research area today. You see all this exciting work coming in this direction. What was the technology then? The technology will usually people put a somewhat of foam-like material, put on top of the water, and then those material maybe wake the water slightly up, and then they put some nanoparticles, absorb the light. Well, there's a problem, right? Number one, you have this foam-like easily get clogged. Number two, well, when you evaporate, the water does have impurity, right? So you have a lot of impurity, you have a salt, you have easily clog it afterwards. Number two, it's a lot of problem issue. Number two, you cannot, this one have to float on the surface horizontally. You cannot orient it into an arbitrary direction, right? So we understand in real world application for sunlight, the sun doesn't stay in one position all day long, right? It's moving around. So how do you really track in the sun motion? There's no way. So basically, although there was a lot of work in interfacial evaporation, but it was more laboratory demonstration. And here we go. Remember, we have this superhydrophilic surface. We can pull the water uphill, and then any direction, vertical, 30 degrees, 60 degrees, we can orient it in any direction, tracking the sun motion. So that's what we did. We have this surface constantly facing the sun, and then it's black, absorb the energy, and then only weak, a thin layer of water, micron thin. So we only heat up the micron thin layer. And then here's the result. We were able to evaporate the water with a ultra high efficiency. So although it sounds starting with it's such a obvious science, water evaporation, but I have to say this is probably as we study this, it's deeper and more complex than anything I have encountered. You know, I've studied atomic physics. I think this is more. There's a lot more physics than atomic physics. Why? We start seeing over 100% efficiency. So what does that mean? That means if I take in all the solar energy, I'm going to calculate it. This energy and how much energy will 100% convert into water evaporation, how much water I will be able to convert. What do I get? I get more than that. Well, you might say this is insane. You are breaking the energy conservation. It turns out not. That's why I'm saying this is a really exciting area. It's such an exciting topic because we start notice when the water pull up on a thin film, it's also changed the intermolecular bond. And that bond allows the water evaporates at a different form, not the bulk water enthalpy anymore. So we start thinking the efficiency goes to 200%, 300%, 400%, just insane amount of efficiency. So let me show you, let me jump ahead. So here's the water in this tube. And the solar light comes in, focus on this. There is a piece of material here. I think let me see. Okay, you can see start water just boiling. That's how efficient it is. Okay, so let me go back and so that's the idea of basically
in much of the world, clean water for drinking or washing hands.
Okay, so that's the idea about how we can do this. I think just on time reason, I'm not going to get too much into this. And this is basically the idea is it can be seen from this cover from the Nature Sustainability. I wrote this full author, full citation here. What I wanted to emphasize, basically highlight is, and our research, not just the PhD senior scientist, we actually have a lot of undergrad students. And you can see from the author list, I highlight this, 40% of the authors are undergrad students who actually done the work, who did a lot of this years of work. You know, you put in, not just put the surface, sometimes we have to put the insulation, we build a foam, we build all the different devices, and then we went up to the top of the Walmart floor and then do the real experiments up there. All right, so let me continue on. So indeed, if we evaporate the water with all the contaminants, and then you can see, so you have a purified water in every categories below WHO stand is below the WHO. Exceed the I'm not sure, exceed the WHO standard for drinking water. Okay, so definitely research is not limited to Walmart or Gergen, and then I think it's a very exciting topic, and we take it to the world. We go to the different continents to collect the ocean water, actually do it with the real ocean water there. So right here, so here is one of the previous students, Eric, went to Ghana to deploy our TEG technology I just discussed. And right there, Dr. Subhash is sitting here and went all the way to the tip of the southmost tip of the African continent. And he will be able to collect in the water. And one leg, one foot, he could stand in the Atlantic Ocean, the other foot he can stand in the Indian Ocean. So one place he can collect the water in both oceans. Indeed, we have to drive away for a few hours to different places. We're not collecting water in one place. Okay, and actually you can see it's not an easy job to collect in the water, and I can certainly attest it's quite struggling when you actually collect in the ocean water. Okay, so let me switch the gear to discuss the other topic, which does not involve lasers and as mentioned, thin film and the photonics. So what do I mean by thin film photonic or thin film nanophotonics? Well, we want to realize a nanophotonic effect with a thin film optical coating. Okay, so if you're looking at the optical coating, is again, as I mentioned earlier, it's a mature technology, hundreds of years, depends on how you trace it, you know, at least the industry-wise over a century. Okay. And but if you count how many types of optical coating do you have, you can count it with one hand. Very few. There's a metallic coating, there's a dielectric coating, and dielectric coating you can have one layer or multi-layers. You either enhance the reflection or either you enhance the transmission. That's about it. There's not much. There's nothing too much. It's very mature, works well, and people don't think too much about it. And actually, just right before the talk, I went to Wikipedia and tried to look it up. And here's the type of coating you have. And then also, this is the type of coating I'm going to discuss today. I think it's revised in the last couple of years in the Wikipedia. That's the coating we introduced from my lab. The two references are both from the lab. Okay, so really a very few type of coating. I think we are adding a new category class of coating here. So the coating we are discussing is called photoresonance optical coating. So what is photoresonance? So there's a very interesting article in Nature Photonics says phano still resonating. And this is in 1961, the first paper discussing looking at the atomic system, you can have a continuous state and discrete state. If they interfere, they can create this the interesting line shape function, the so-called final resonance. And later on, it finds a way into a more nanophotonic application. By realizing this, you either use plasmonic resonance system or use a metal material like this resonator. In either case, very complex. Again, E-beam lithography, you make this system and then you're looking at these effects. So that's where we come in. We said we can actually do this. Well, if we don't do this from the Institute of Optics, where should we do this? Right? We know this old technology, optical coatings. So you can actually put, the key is having the broadband absorber and narrowband absorber, integrate this together. We can integrate with coating. So the top layer is a broadband coating. So you can, what will give you broadband if you have a lossy dielectric, typically germanium, put it on top of a metal layer, silver, then you have a broadband absorber. And the bottom, the narrowband absorber, this is easy, right? So laser cavity, Peripheral Pro is a narrowband absorber. So some types of this MDM, metal dielectric metal layer. Okay? So we put this together, and then we got this reflection, this final resonance layer. So here's some simulation. And then what you see is a narrow band reflection. So extremely narrow band give you then what do you have if you have a narrow band? You have a very, very pure color, right? Narrow band reflection is a reflected color. And then so you can see it's very colorful and more interestingly, so the coating is reflect. We can design the coating, have it 50% reflection, 50% transmission, or you can have a full reflection. I can design whatever I want. Okay, so but the interesting thing is the transmission and reflection will be the same color for this coating. You might not really appreciate, but for most of the other optical technology, it can be same color. So let me just show a quick video here, just show this effect. This is a bit slow. Will come. Okay. All right. So the reflection and transmission, same color, if you pay attention to here, but I want to contrast and see what do I mean by different colors. So this is typical coding, right? So reflection and transmission, different colors, very clear. So now you notice what I was talking about. This final resonance optical coding, same color transmission, this has never been able to, no other technology was able to, coding technology will be able to do that. Okay, so you do have, currently we do have a narrowband refraction, typically multi-layer Bragg reflector type, right? So usually you have to have a low refractive index, high refractive index, low, high, you alternating many layers. So with the, how many layers do we have for frogs? I'm going to call this frogs, final resonant optical coding. Okay, 4 layers, very thin. Okay, with only 0.2 micron, we can achieve this narrowband refraction. How can you, if you use a Bragg reflector, what's the comparison? With 1.9 micron, 10 times thicker, you will be able to get this narrowband refraction, but much broader band. If you want to narrow that, you have to go to 10 microns. Huge difference, even just for the narrowband refraction. I think this is on the way. We do believe this can display a huge amount of applications for narrowband refraction, let alone there are properties if we need it.
Question.
Yeah.
If both the reflection and transmission are narrow band, the rest of the frequencies have been absorbed, they will have been absorbed by the broadband absorber or something?
Yes, absorbed. Yes. Yeah. So so the video, I just need to showcase that one. Let me move on to okay. As I mentioned, I'm going to focus on energy applications. So here's the example. So there is again, solar energy application. There is a solar hybrid thermoelectric power generation. What it does is the solar energy comes in. You can reflect the solar spectrum to your silicon solar cell, and then harness the thermal energy by other things. But there actually current technology does have challenge for this. Usually you have a beam splitter, okay, spectral beam splitter reflecting a certain spectrum to the solar cell and then heat up the rest. But the problem is your beam splitter most of the time has this usually current technology at least, you just reflect everything above the band gap to the solar cell. And then there's a problem for this, right? So you do get this the solar cell energy, photon energy you need, but you also overwhelm with the heat. You have a lot of unused energy. So what we do here is again, narrowband reflector. We were able to just reflect the narrow band to the, I don't know, this one's keep advancing cell. Narrow band to the PV cell, and then the rest we can utilize the thermal energy for other applications. And I also highlight some of the undergraduate, just like I didn't talk about every single paper, but I think for some of the big papers, and we have a quite a bit undergraduate participations. And here's a follow-on work just published a few months ago. on the frogs. So because we have this very vivid colors, right? So we were able to start producing all this color palette. And if you start to study color science, you know this graph and CIE chromaticity diagram. So showcase where your color is. The more towards the edge, the more pure your color is. So we show this color, we can create the RGB. I think the projection lose the color fidelity. This is really blue. Okay, doesn't look as blue, but it's actually very blue. And then so we were able to produce this color palette, and then we can go around this chromaticity diagram, really pushing towards the edge. It's impossible to go towards the very edge that needs the laser pure color, but this is so far incoherent light, the highest color purity we have demonstrated. And then we compare with all the other technology and listed there, they are all smaller in the diagram. In terms of Fabric Pro cavity, nanophotonic cavity, all these other technologies, the frog create the highest coverage of the color purity, okay, and nearly full gamut. So with a very minimum time I have, I'm going to just discuss one last thing. And once we have this optical coating, we also wanted to ask the question, can we utilize it to manipulating other materials and as a thin film platform? So now there are a lot of materials out there, right? So everybody knows 2D materials and more advanced materials. And there's one called perovskites. If you're in solar energy, this is really the poster boy of the solar energy, because it's very cheap and people project it will be display silicon in years ahead. And it's as a fraction of the cost of silicon, but it does all these amazing things. But the problem is there's a lot of research still going on. And here are some application of perovskites. And so typically, if you modify perovskite, it's a very chemical involving work. People use different types of, if you're looking at this formula, and it has, people use different chemicals and come up with some composition. Hopefully, it will give you highest efficiency. So what we do is, we are a physics lab. We want to develop a platform technology and see if we can increase the perovskite efficiency. And that's what we have. We put the perovskite on the nanophotonic thin film coating platform we developed it. Well, first case, people say, if you understand how the interaction works, usually that will, if you have the perovskite, have the electron hole pair generation, will make the decay faster. Why? Because the substrate providing additional channels to dissipate the energy. Okay, this is a little bit more physics than I have time for it. So just take my words for it. Intuitively, if you put a platform, you speed up the decay. But what we saw is totally opposite. So we put a platform on the perovskites, and we see it's dramatically slowed down the decay. This is good for what? Detector and solar cells. You want to create the electron hole pair and hold it there. You don't want it to come back and recombine together, and then you can create the current, right? So the solar cell detectors. And what we saw is dramatically slow down the decay. And what's going on is a lot of physics to it. We actually use the substrate to create this image charge. The image charge somehow cancel out the dipole moment, and then really just cancel out this dipole and then slow down the process. So in this demonstration, we demonstrate over about 250% increase in the light conversion in solar cell, and it should work the same principle as for detector and the solar cells. Okay, so as I mentioned, there's this is my lab. Definitely, the work is carried out by so many students and postdoc and research scientists, really putting all the hard work into this the topic I was discussing with. And also, I mentioned not only we have a lot of PhD postdoc and senior scientists, but we also have a large undergrad students who done quite a bit work for a lot of exciting work. I think we have been carried out, and I also this is certainly just give a acknowledgement to the funding agencies we have, and also as Golan mentioned, I'd like to just put this last slide here. And Subhash and I actually we published this added this handbook, CRC handbook for laser technology, published 2021, full volume. I think today is the most comprehensive ones in laser and technologies. All right, so that's all for my talk. Thank you for your attention.
All right, there are lots of interesting things. I'm sure there will be some questions in the audience. Let me see if anybody wants to ask anything. Okay, Andrew.
But like going back to some of the early stuff you said, can you give us a sense? You talked about how these lasers could produce these incredibly organized, very small scale things.
Yeah.
We didn't really get a sense of whether that was something a single exposure could do without moving the laser. Do you have to move the laser?
Oh, you're okay. That's
give us some sense of how that order gets created.
Yes, very good question, Andrew. So we can do both. Usually, when I show that is involved multi-laser exposure, and sometimes we have to scan the laser beam to cover a larger area, which is a good thing. We want to cover a large area. Mm-hmm.
So how does moving it smoothly, what is it that creates the ordered discrete structure if you move a laser smoothly?
Right. So usually that actually could happen for a single beam. So for example, there's some of the mechanisms, there are a lot of mechanisms. Some mechanism, it could be our laser beam comes in large surface plasma. That surface plasma can interfere with the tailing of the laser pulse, and then they create this structure. So those mechanisms could happen in single pulse, but we can move them around. Yeah.
Can you go back to the perovskite for a second?
Okay. So which one do you want me to?
Yeah.
This one? Okay.
Whatever
you talk about the substrate or the top perovskite layers? The top layer? Oh, you can make it bulk as thick as you want.
Sorry, the functional layer that.
Oh, the lower layer is again, what is really matters is the nanometer scale, 10, 100 nanometers, and your substrate can be very thick, right? It's just the glass. Mm-hmm.
Anyone else? Yeah.
You mentioned with the nano reflectors that the color of the transmission and the reflection are the same. Did I understand correctly?
Yes.
But how do we have conservation?
Oh, so we are so you can control how much transmission you go forward, and basically I can if I have this lower metal substrate. If I make it very thick, nothing will transmit. 100% reflection. Okay.
So basically, R plus T plus A is still.
It's still one. Yes, I'm not breaking the energy.
Yeah.
So
in the situation,
well, the absorption they added up to be one.
no, but so how much efficiency is in the reflection? So you had a certain amount of light, say 1 milliwatt going in.
Right.
How much reflection efficient versus
Yeah. So we will make the layer so very low absorption. In that case, you can approach 50-50. That's the best case, right? So it's still some absorption. Well, if you can make it a little bit lossy, maybe you have some. So I can have 10% reflection and maybe 50% transmission, and then the remaining will be absorbed. So three components adds up to be one. We're not breaking the energy conservation. Yep. Yeah.
I think I remember speaking to students in your lab group, they talked about the paper where the surface is, but like, I guess this is
Right. So, well, it depends on, so we have done, for instance, we make hydrophilic, hydrophobic surfaces. We actually done durability tests. And the durability test, we had a test, for example, working with Boeing, okay, large. They did the abrasion test, meets their standard for anti-icing applications. So we can preserve and the durability actually cycle after cycles and the test. Well, nothing can stay forever. If you use a hammer and try to destroy it, you will destroy, right? So it depends on type of applications. So for typical wear and tear, I think it will be fine. But if it's very, very aggressive abrasions, and you will destroy everything.
Anyone has a question on Zoom? If you have a question, please feel free to ask at this time.
I saw some like a chat Q&A.
That's chat. I don't see anyone here.
Oh,
I had one. Yeah, go ahead.
oh, Jen.
Yeah, go ahead.
So when you're talking about those
It's not here.
narrow band paths, can you hear me?
I don't need to turn on.
No, I think they may be here. Yeah, Jen, can you go ahead again? We could not hear that.
Oh, okay. Can you hear me now?
Hello, Jen?
Hello.
Or you can type it if you want. I can read it.
Okay. So
There's also a question here.
Yeah, we can hear Jen. Jen, you want to ask a question? You can't hear us. I don't know why. I don't understand.
yeah, can you hear me?
This is on. The sound is not coming.
Can you see my?
Well, we could not hear you, Jen. There's some problem with the sound here. Would you if you want to type on the?
Yes, she asked, the question was asked about instant angle.
Oh, incident angle. The question was asked about incident angle.
Do you want to be more specific? Yeah, by the way, I saw some message. Well, we can read it from the chat.
Okay.
Do you want to be more specific, or you just want me to make some general comments? Or is this relates to the final resonance optical coating, I assume?
How sensitive are your narrow filters to the incident angle?
Yeah. So this is so there's a question about instant angle dependence for the optical coating. Actually, we have a slide for it. Yeah, I wasn't able to just because time limitation, I wasn't able to get into a lot of details. Each work there's so much detail. I certainly couldn't get into it. I think Jen. So looking at the slide, so we can actually again design and control the iridescent effect. This is the so-called iridescent effects about the instant angular dependence. So you can see if we use this layer, if we replace the layer. So we have two studies. One uses a titanium oxide layer, and the other one uses magnesium fluoride layer. Titanium oxide has a higher refractive index than magnesium fluoride. So we can see this one, that's the wavelength versus instant angle, has very essentially no dependence. We can make it angular independent. That's important for some type of solid color. So I'm looking at this surface at any angle, I can see the same color, angular independent. So on the other hand, I can make it angular dependent. Okay, you can see that's actually changed with angle.
There's a question from Sujana Marcos.
Mhm.
She said, could you share your experience and tricks that help your research to be fit by big media outlets, the New York Times and CNN? So what is the trick behind that? Your experience about
Okay. Who asked the question? Oh, okay. There's not much trick. I think it's just maybe at the beginning we had this exposure, and then I think perhaps the medium is just seems to be interested in any following up work, and somehow we got into it, and then later on whatever we have, they somehow are interested. Yeah, so they actually sometimes inquire for it. Yeah.
So you are partly lucky and partly work. I mean, both. It's both the luck and the work.
So those both, right.
Okay, please.
With respect to the efficient evaporator, you mentioned how the previous solutions of the foams were prone to clogging.
Yep.
Why isn't the machine surface prone to clogging? How does it avoid that issue?
Yeah, so very good question as well. So basically we have a surface, right? So it's our capillary structure is exposed to air. So it's a surface. The previous structure is a foam. They have all the holes inside this foam. Once you do a little bit desalination or purification, you get the salt clogging up all the pores. But we have this open surface. Two things. Number one, if there was any clogging, we can wash it out later on. We can spray it, wash this out, right? Very easy to maintain. But what's more interesting, but I don't think I can say too much, that is a research is under review of Nature Nanotech. Right now we have a big paper and we particularly address that problem, and we actually can eliminate the deposition, the clogging from start. I just can't get too much into it because it's under review right now. Yeah. Come back with check with me in a few months. Hopefully, by that time I can give you a paper to read.
We have one more question here.
With the laser-based optical coatings, obviously you're able to tune somewhat the response because you can change what colors are reflected.
You said laser-based coating or the final resin
metal.
Oh, okay, yeah.
Are you able to make resonance structures with that? How fine is your control? Can you make diffractive optics or metamaterial-like structures, or is it more broadband sort of processing?
No, we can make a broadband absorber black metal. We can also make specific colors, and we can make a blue. We can make a reddish colors, and they're not as narrow as, for instance, here, but they are single. You can see the color, somewhat narrow.
What sort of line widths can you absorb? How narrow can you make those screws?
So we usually, that is not very narrow, and it's hard to make it very narrow, not like this type of filters for sure. And usually tends to 100, maybe hundreds nanometers, okay, but they give you this color effect.
Okay. I don't think I see any other questions, so let's thank Chunlei once more. Yeah. Thank you. Well, very interesting.
Thank
And very, very fruitful, very, very interesting.
Oh, thank you.
Yeah.
Thank you.